Welcome back to the deep dive. Get ready, because this time we're going to be exploring in latent reasoning attention heads.
Oh, yeah?
We've got a stack of research papers here. They're causing quite a stir in the field.
For sure.
And these papers, they really dive deep into how large language models reason and how they learn from the context they are given.
Yeah, it's an exciting time to be following this. And these papers, they really offer a fascinating glimpse into the inner workings of LLMs.
Think of this deep dive as a crash course on the latest breakthroughs in, LLM reasoning.
Yeah.
Now, you already know attention heads are key players in the transformer architecture.
Right.
But today, we're going to zero in on a specific type. They're called in latent reasoning attention heads, the paper attention heads of large language models, a survey.
Yes.
It dives into how these heads are categorized
Yeah.
and how important they are for an LLM's problem-solving abilities.
Yeah. What's fascinating is that the survey highlights how understanding these attention heads could be the key to enhancing, LLM's ability to reason and solve problems more effectively.
Yeah.
For instance, the survey cites papers like Emergent Abilities of Large Language Models and Language Models are Few-Shot Learners,
Right.
which show just how crucial LR attention heads are.
It's like cracking the code of how LLMs think.
Yeah.
So let's talk about function vectors.
Okay.
The paper Function Vectors in Large Language Models dives into this, right?
Yes, and they make a surprising discovery. They found that these function vectors, which are essentially vectors within the model that represent specific input-output functions, they can actually be extracted.
Wait, hold on. So it's like we can pull out these little packets of instructions that tell the LLM how to perform certain tasks.
Exactly. And here's the kicker. These extracted function vectors can then be used to trigger those same tasks, even in completely different contexts than where the LLM originally learned them.
That's wild. So the LLM isn't just memorizing, it's learning
Right.
generalizable functions that it can apply to new situations.
That's what the research suggests. The authors of Function Vectors in Large Language Models tested this across a variety of tasks, like finding a word's antonym, capitalizing letters, and even translating between languages. These function vectors retain their power, even in zero-shot settings and when given natural language instructions.
That's a game changer. If we can figure out how to manipulate these function vectors, we could potentially teach LLMs to solve entirely new problems without having to train them from scratch.
Absolutely. It opens up a whole new avenue for controlling and enhancing LLM capabilities.
Wow.
But there's another layer to this. Function vectors in large language models goes on to argue that these function vectors aren't just correlations, they are causal.
Okay, break that down for me. What's the difference and why does it matter?
Think of it this way. Correlation means two things tend to happen together, while causation means one thing directly causes the other. In this case, it means that manipulating the function vector directly causes the LLM to perform a specific task. It's not just an association, it's a direct control mechanism.
So it's like we found the levers that control how the LLM processes information.
That's a great analogy. Now, this research is particularly interesting because it differs from previous attempts to represent tasks within LLMs.
Okay.
You may recall earlier studies that tried to introduce task representations using things like meta mappings or code books.
Yes, those techniques always felt a bit like trying to force the LLM to think in a certain way.
Exactly. But function vectors are different because they already exist within the model. We're not adding something artificial. We're discovering and harnessing something fundamental to how LLMs learn.
It's a much more elegant approach, for sure. Now, function vectors in large language models goes into some really cool examples of these function vectors in action, right?
Yes. One of the most fascinating examples is the cyclic behavior they observed when manipulating certain vectors. They found that when they added or subtracted certain function vectors, the LLM's output would cycle through a series of related words.
Cyclic behavior. That sounds a bit like a linguistic merry-go-round.
It does, doesn't it?
Yeah.
In the antonym task, for example, they found a function vector that, when repeatedly added, would cycle through a word, its antonym, then back to the original word, and so on.
So the LLM is basically getting stuck in a loop of opposites.
Yes.
That's both amusing and slightly creepy. It's almost as if the model is learning relationships between words, and those relationships govern its output.
Right.
They found this with other tasks, like identifying the next item in a sequence, right?
Yes. They observed similar cyclic behaviors in other tasks. This suggests that LLMs aren't just understanding individual words, they're learning complex relationships between them, a sort of internal logic that governs how they process language.
So these function vectors aren't just simple semantic offsets. It's not just moving between words that are close together in meaning.
That's a great question. Interestingly, function vectors in large language models ran experiments to rule out that possibility. They found that simply adding or subtracting semantic vectors didn't produce the same cyclic behavior as manipulating the function vectors.
So there's something more to these function vectors than just semantic similarity. There's a deeper level of understanding embedded in them.
Precisely. And that complexity is what makes them so intriguing. They appear to encode a deeper understanding of relationships between words and concepts. In fact, the structure of these function vectors revealed information beyond just the output vocabulary.
They hold more information than we initially thought.
Yes, they're not just a dictionary of words, they're a roadmap of the relationships and rules the LLM uses to process information. And that's what makes this research so groundbreaking. It gives us a new way to understand how LLMs learn and reason.
Now, there's another type of latent reasoning head that we need to discuss: induction heads. How do these fit into the picture?
Well, in-context learning and induction heads suggest that induction heads, which are known for their role in in-context learning, also fall under the umbrella of in-latent reasoning heads.
So it's more about how these heads are used and what they're focusing on rather than them being completely separate entities?
Yes, it's like different tools in the same toolbox.
Okay.
And the intriguing part is that this paper proposes that induction heads might be, well, the primary mechanism behind in-context learning, especially in small models.
Wow, that's a bold claim. They're suggesting that these induction heads are the key to how LLMs learn from the examples we give them.
Exactly.
That is fascinating. Can you tell me more about the arguments they use to back up this claim?
Of course. The paper presents 4 main arguments, all backed by empirical evidence. First, they talk about phase change alignment. They observed this fascinating phenomenon where the model's in-context learning ability suddenly jumps during training, almost like it's having a eureka moment.
So it's like a light bulb suddenly switching on.
Exactly. They found that this jump often coincided with the emergence of strong induction heads.
Okay, but correlation doesn't always mean causation.
Right.
Is there more to it?
Yes. Their second argument, macroscopic co-perturbation, addresses that.
Oh.
They tweaked the transformer architecture in ways that affected the formation of induction heads. And guess what?
What?
The architectural changes directly impacted the model's in-context learning abilities.
So by manipulating the conditions for induction head formation, they could directly control the model's ability to learn from context.
Yes, it's like they found a way to fine-tune the model's learning process. Their third argument involves ablation studies, where they removed or deactivated induction heads in smaller models and observed what happened.
Right.
The model's ability to learn from context plummeted.
That's pretty convincing. It's like removing a vital component and watching the whole system fail.
Right.
What's their final argument?
They call it induction head generality. Initially, they define induction heads based on their ability to copy literal sequences.
Like a parrot mimicking sounds.
Exactly. But their research revealed that induction heads are capable of much more than just rote copying. They could generalize that copying behavior to learn more complex patterns and relationships.
So these induction heads are more sophisticated than we thought?
Yes. They're not just copying, they're figuring out the underlying rules. And that's why this fourth argument is so important. It suggests that induction heads can drive more complex forms of in-context learning than we initially believed. And they provide a really compelling example of this using the first paragraph of Harry Potter. Remember the phase change where the model's in-context learning suddenly improved?
Yeah, it's like the model suddenly got how to learn from the Harry Potter text.
Well, before the phase change, the model struggled to predict repeated sequences from that paragraph. But after the phase change, its predictions became significantly more accurate. And this coincided with the strengthening of induction heads, further linking them to this crucial learning ability. To understand how these induction heads actually work, the researchers in context learning and induction heads took a deep dive into their inner workings, kind of like reverse engineering a complex machine.
So they basically dissected these induction heads to figure out what makes them tick.
Exactly. They used synthetic data sets and controlled experiments to isolate and study induction head formation and behavior. They were even able to manipulate attention patterns within the model to pinpoint the role of induction heads in the learning process.
It's like shining a spotlight on a specific part of the stage to see how it contributes to the overall performance.
Yes, and what they found was evidence suggesting that these heads were learning by copying patterns, but with a unique twist, they called it fuzzy prefix matching.
Fuzzy prefix matching. Sounds intriguing.
Think of it like this. The induction heads are looking for similar patterns, but they don't require an exact match.
Oh.
They allow for some flexibility, which makes them more adaptable.
So it's a more robust form of pattern recognition that can handle variations in noise.
Precisely. And they ran more ablation studies, this time focusing on this fuzzy prefix matching mechanism. When they disrupted that mechanism, the model's in-context learning performance tanked again.
Oh, wow.
This suggests that it's not just the induction heads themselves, but this specific fuzzy prefix matching that makes them such powerful learners.
So they've essentially uncovered the secret sauce behind these induction heads. And I see we have another paper that seems to be building on these findings. Induction heads as an essential mechanism for pattern matching in context learning.
Yes, this paper provides even more evidence for the crucial role of fuzzy prefix matching in context learning. They conducted experiments specifically focused on the contributions of induction heads to in-context learning, ICL, in large-scale, widely used language models. Their ablation studies demonstrated a significant drop in ICL performance when induction heads were removed or their functionality blocked.
So no matter how they approached it, disrupting the induction heads messed with the LLM's ability to learn from context.
Right. They also delved into how this fuzzy prefix matching and copying mechanism works at the token level, where the real magic happens.
So they looked at how these induction heads are processing and manipulating the individual building blocks of language.
Yes, they observed that induction heads use this fuzzy prefix matching to identify and copy specific tokens from the context, essentially piecing together patterns and information to create the output.
So it's like these induction heads are acting as tiny pattern recognition machines, scanning the text for relevant bits of information and then stitching them together to create a response. This is all getting pretty complex. What's the big takeaway for us who are just trying to keep up with this rapidly evolving field?
The key message here is that we're finally starting to understand the mechanisms behind in-context learning, one of the most impressive capabilities of LLMs. We're moving beyond just observing that LLMs can learn from context to actually understanding how they do it at a fundamental level.
So we are gaining the ability to not just interact with these LLMs, but to shape their development and guide their learning.
Exactly. Now, let's shift our focus to a paper that dives into the nitty-gritty of how these induction heads develop over time. The evolution of statistical induction heads. In-context learning Markov chains. This paper uses Markov chains, which are mathematical models for analyzing systems that transition between different states, to understand how induction heads evolve as they are exposed to new information.
So they're using a simplified model of the learning process to study how these induction heads become such impressive pattern recognizers.
Yes. And they found that induction heads show a simplicity bias. They tend to favor simpler solutions initially, even if those solutions aren't the most accurate.
So it's like they start with a basic understanding and then refine that understanding as they encounter more data.
Exactly. It's a step-by-step learning process. They also found that this simplicity bias can actually hinder the learning process. If the model gets too stuck on the simpler solutions, it might take longer to discover the more complex but ultimately more accurate patterns.
Interesting. So there's a delicate balance between starting simple and being open to more complex solutions. It's almost like watching a human learning.
It is, and that hints at a deeper connection between how LLMs and humans learn. Now, another key finding in this paper is the importance of alignment between layers. They observed that the transition from simpler to more complex solutions often involved a sort of synchronization between different layers of the model.
So it's not just individual induction heads working in isolation. It's about how different parts of the model collaborate to make this learning process happen.
Yes. They found that different layers seem to learn from each other's progress, suggesting a type of feedback loop or collaboration. They even illustrated this with a simple model with just 2 layers. The weights of the second layer converged toward a specific pattern, and that pattern then influenced learning in the first layer, leading to a jump in performance.
It's like one layer is setting the stage for the next layer to make a breakthrough. It's teamwork at the neural level.
Indeed. And this paper also touches on a critical aspect of LLMs, their ability to handle different data distributions. Remember, data distributions refer to the different types of data an LLM might encounter in the real world.
Right, like the difference between understanding text from a news article versus a social media post.
Exactly. They found that LLMs can display different learning behaviors depending on the type of data they are exposed to. They experimented with manipulating the information content of data sequences and observed how the model's learning dynamics changed.
So they're basically testing how the model adapts to different types of information.
Yes, and what they discovered is that the model actually learned faster when the data wasn't overly simplistic. It's like the model is more efficient when it has to work harder to find those complex patterns.
So it's like training an athlete. Sometimes you need to push them harder to help them reach their full potential.
Yes. And this has significant implications for how we design training data sets for LLMs. We might need to be more strategic about the complexity of the data we feed them to encourage the development of these sophisticated learning mechanisms.
So we're not just aiming for pattern matching. We're aiming for true problem-solving abilities.
Exactly. We want LLMs that can generalize their knowledge and apply it to new and unseen situations, not just repeat what they've been trained on. To explore these learning dynamics further, the evolution of statistical induction heads. In context, learning Markov chains analyzed a very simple model with just 2 states.
2 states? That sounds incredibly basic.
It might seem simple, but even in this minimal setting, they observed fascinating behavior. They tracked the evolution of the model's weights over time, visualizing how those weights in the second layer influenced learning in the first layer, specifically the positional embeddings.
Positional embeddings, those are the vectors that tell the model the order of words in a sentence, right?
Yes, they help the model understand that dog bites man is different from man bites dog.
Right, because word order changes meaning.
Mm-hmm.
What did they find out about these positional embeddings?
During the training process, the positional embeddings developed an unusual even-odd pattern. The embeddings for even-numbered positions differed from those for odd-numbered positions.
An even-odd pattern. That's strange. What does it mean?
That's the big question. The evolution of statistical induction heads. In context, learning Markov chains doesn't give a definite answer, but they speculate that it might reflect how the model learns to process sequential information. Perhaps it's a way for the model to distinguish between different states based on their position in the sequence.
So it's like the model is creating its own internal code for understanding the order of events.
Precisely. And this finding reminds us that LLMs can develop their own ways of representing and solving problems, which might not always align with our expectations. To support their findings, they presented a series of propositions and mathematical proofs, essentially building a bridge between what they observed and the mathematical principles that govern those observations.
So they're providing the theoretical foundation for their empirical observations.
Yes, it's rigorous science, combining observation with mathematical proof.
It's amazing to see how these researchers are piecing together a deeper understanding of how LLMs learn.
It truly is remarkable. And the evolution of statistical induction heads. In context, learning Markov chains. Well, they emphasize that even within their simplified model, they observed diverse learning behaviors, indicating that there's still so much we don't know about induction head development.
So even with these insights, we're still just beginning to explore the complexities of LLM learning.
Absolutely. They encourage more research into different model architectures, training data sets, and evaluation metrics.
Right.
To gain a more comprehensive understanding of induction heads and in-context learning. They also highlight the importance of studying how different learning mechanisms interact within the model, not just induction heads in isolation.
It's like we're assembling a complex puzzle, and we've found some key pieces, but there are still many more to discover.
That's a great analogy. And speaking of delving deeper, what needs to go right for an induction head? A mechanistic study of in-context learning circuits and their formation takes an even closer look. At the specific circuits and mechanisms within these induction heads, they utilize a fascinating artificial optogenetics framework to manipulate and study activation patterns within these heads.
Artificial optogenetics. That sounds like something out of a science fiction novel.
It's a clever technique inspired by optogenetics, where light is used to control neural activity in living organisms. In this case, they use a computational framework to activate or deactivate parts of induction head circuits, enabling them to isolate and study specific mechanisms.
So it's like they're using a virtual tool to precisely examine different parts of the induction head and see how they contribute to learning.
Exactly. They use this framework to study induction head formation in transformers trained on a simple few-shot learning task, focusing on a type of induction head that learns to copy input labels to the output, which is crucial for in-context learning. They identify 3 key subcircuits within the induction head, each playing a specific role in the learning process.
So there's a whole hierarchy of processing going on within these induction heads, with different components working together to enable in-context learning.
Yes, and they meticulously study these subcircuits and their interactions. One subcircuit, which they highlight as particularly important, is responsible for copying input labels to the output, essentially mimicking the examples provided in the context. They observe that this copying mechanism emerges gradually during training and is tightly linked to the overall performance of the induction head.
It's as if we're witnessing the induction head learning to copy, like a student practicing a new skill.
That's a great way to put it. And their experiments revealed that this copying subcircuit learns more quickly than some of the other subcircuits involved in pattern matching.
So the induction head masters the art of copying before it develops its more complex pattern recognition abilities.
Precisely. They also explore how these learning dynamics are affected by factors like the number of classes and labels in the training data.
So they're essentially testing the limits of the induction head's learning capacity and how it handles increasing complexity.
Exactly. They found that increasing the number of classes or labels can delay the formation of induction heads, but for different reasons. Increasing the number of classes makes it harder for the head to pinpoint the correct label based on the context, while increasing the number of labels makes the copying operation itself more challenging.
So different types of complexity in the data pose distinct challenges to the learning process.
Yes, and that's why controlled experiments are so crucial. They allow us to isolate and understand these intricate dynamics. Now, what needs to go right for an induction head? A mechanistic study of in-context learning circuits and their formation goes beyond just its findings on induction heads. They introduce valuable tools and methodologies for the field of mechanistic interpretability. Their artificial optogenetics framework, which they call clamping, allows for precise manipulation of activations during training, providing a powerful tool for studying causal relationships within the model.
It's like they've given researchers a new toolkit for dissecting and understanding LLMs.
Yes, and they argue that this clamping approach is particularly advantageous for studying learning dynamics. It enables researchers to observe how circuits and mechanisms evolve over time, revealing how they contribute to the learning process.
It's like we're transitioning from static snapshots to dynamic videos, gaining a much richer understanding of how these LLMs learn.
Exactly. And they're excited about the potential of combining this clamping method with other powerful techniques to further unlock the secrets of LLM learning.
It feels like we're on the verge of a new era in LLM interpretability, where we're moving beyond simply identifying components to actually comprehending how they learn. And how we can influence that learning.
I couldn't agree more. These papers demonstrate the tremendous progress we're making in understanding these incredibly powerful AIs. We are moving closer to the goal of not just building intelligent machines, but truly understanding the very nature of intelligence itself.
It's a journey filled with both challenges and immense possibilities. As we continue to delve deeper into the world of LLMs, who knows what we might discover? Perhaps we'll uncover new learning mechanisms, develop innovative training techniques, or even unlock the secrets of consciousness itself.
It is a truly exciting time to be working in this field.
Well, that concludes our deep dive into latent reasoning attention heads. We've covered a lot of ground today, from function vectors to induction heads and the intricate mechanisms that drive in-context learning.
We've only just scratched the surface, and there's much more to explore.
Speaking of exploring, next time we'll be diving into expression preparation attention heads. Buckle up, it's going to be another fascinating journey into the depths of LLM reasoning. Until then, keep those neural networks firing.